Right, I do that. Right, so disclaimer up front, if you expect a lot of science, that's not going to be it, right? Shantanu asked me to give a talk, and I said, okay, I've got this talk lying around I gave in January when we sent Steve Ferber off into final retirement. And yeah, Shantanu was like, that's a cool talk, so everybody knows where the whole story is really coming from. So you get those slides, right? Going on a SpiNNaker 123 journey with Steve Ferber, kind of a Dresden perspective. Right, for those who don't know me, I head up a group in Dresden University, Technical University, about 40 people, 45, a lot of designers, algorithm people, right? Because we really need to handcraft that stuff for our machine, or machines plural. We also have a line of neural implants, so I've actually got medical people on my payroll, and yeah, we all get excited about chips, but the general public doesn't get it, so we need a robot, so that's why I also got roboticists there, right? You need something moving around. And we've got our, what I call our biotope spin-off, so 5 spin-offs, about 250 people. I get back to that later, why I say this is a biotope. It kind of gives us the ability to do things we couldn't do as a simple academic chair. We focus very much on really the system on chip. So not single components, we do all those, right? A lot of high-speed communication, general processor design, advanced CMOS design, like adaptive body biasing, neuromorphic circuits, neural interfaces, AI, but very much towards the system, which basically means we don't kind of put every single component on the edge, because it's a surefire way of the overall system not working. I mean, this is simple error analysis will give you that. So we very much always design a system top down. We do this quite often, right? A lot of tape outs, 3 to 5 per year. And even before SpiNNaker, our stuff was used externally as kind of science machines. So, for example, the software-defined radio platform processor chip we did. And right, with SpiNNaker, we actually cover 14 orders of magnitude in design. So from the single chip, basically, to a machine that has 10 to the 14 transistors. And nobody expects Saxony to actually be the 5th largest ICT location in the world, right? It's always been this hidden gem. So people, when they talk about Europe and semiconductor, it's like Leti, it's IMEC, whatnot. Yeah, basically we've got 5 times their volume, but somehow Saxony was always this, yeah, are they doing semiconductors? Which kind of has changed now with TSMC coming there, with finally on people's radar. Actually, who gets the reference, by the way, the picture? Okay, cool. Now that, right, you give a talk in the UK, you got to put in Monty Python humor. This is the sketch when some guy comes in, lady starts asking him all kinds of questions, and he's like, I didn't expect the Spanish Inquisition here. And then those guys jump in and say, no one expects the Spanish Inquisition. You should look it up on YouTube. Right, so the life of Brian, aka the brain, meaning SpiNNaker 123. So Steve, he got started back in academia in 1990. He took on this chair at Advanced Process Technology chair at University of Manchester. Before he was with Acorn, right? Which was an interesting story in itself, how ARM came to be. Actually learned that in January because there was lots of ARM history and how the company got to be. The fun part is those guys wanted to design a microcomputer, the BBC Micro, and they wanted a processor for it. And they went shopping in the US, and Intel and whatnot, they claimed totally ridiculous numbers to give them a processor, their own design, right? And then they went back and said, this cool new thing, reduced instruction set computing, we can actually do this ourselves because the processor gets a lot simpler. So ARM actually in the beginning was just kind of the microprocessor for this BBC Micro kind of educational computer that they wanted to do. And then people came up to them and said, this is seriously cool what you did with the processor. Why don't you make an IP business out of it, right? So in startup parlance, right, they pivoted a number of times in terms of their business model, which was kind of interesting. So he went back to academia. He did kind of asynchronous ARM designs, custom ARM designs in those 14 years since then. We got started in '96 in Dresden as an endowed chair by Infineon, my predecessor, Rini Shivny. And this was also specifically, Infineon was very much interested in neuromorphic image sensors, neuromorphic kind of higher level processing, information processing. So we did quite a lot of chips together with them. Actually, 2003. So that's when I came in. I did my master's thesis then. And actually, I get asked it a lot. Where do those guys in Dresden kind of pop in all of a sudden? Why are they doing SpiNNaker too? We've been around the periphery of this neuromorphic community for ages, right? It was kind of very strange things we did, those physics-based, the physics guys in Infineon, they were always interested in points of criticality, wave phenomenon and whatnot. So it was a kind of rarefied thing. But for example, the neuromorphic image sensors, actually, two of the guys who co-founded Prophecy, Christoph Posch and Daniel Matulin, they actually got started with the Infineon image sensors. So Daniel Matulin, for example, he's chief chip designer, whatever at Prophecy. He did his PhD thesis in Dresden 2 years ahead of me. We actually measured chip together. So we think around this periphery. It's just that there's a funny phenomenon. In East Germany, the semiconductor stuff was very compartmentalized, very cloak and dagger type stuff. So people didn't really publish, and this carried over, right? The only thing we ever did publish in those 14, kind of until 2004, was these kind of local German publications. So no one really had us on the radar, kind of. Okay, so in 2005, Steve got this grant, EPSLC grant, to get started on SpiNNaker. And 2004, we got started with the Heidelberg guys on the brainscale system. So that was the predecessor to the brainscale project called Facets. So Heidelberg was doing the neuromorphic chip. We were doing the external communication chips. Call this the asynchronous phase, right? We hadn't yet met up with Steve. 2009, he did his final chip tape out of SpiNNaker 1. 2008, we did the digital network chip, so this chip for the wafer. Right, 2012, we also did our first kind of large processor chip for the software-defined radio platform. And Steve had the first 48 node boards available. And actually already here, we got to know Steve because he was coming into the Brainscales project as an external observer. So we got into first talking things, and this led to essentially at the beginning of the Human Brain project, we decided to team up because we had all this kind of bottom-up process design knowledge, and so we were very much down in the transistor and scaling it up, optimizing the physical interconnects and whatnot. And Steve is more of a computer science guy, so he did the architecture stuff, right? So we had one famous meeting in Manchester where we presented our stuff, he presented his, and Steve then said, seriously, cool, we do this together. Right, so that's synchronous phase. 2015, we had the first kind of SpiNNaker 2 prototype, Santos. This was us on the Dresden side still kind of feeling our ways into the system. Fun fact verification for the Santos. We, of course, verified the processor in simulation, right? Ran kind of virtual programs on it, but only ever small programs. So when we got the chip back, it was like we tried to load the instruction memory, and we couldn't access the upper half of the instruction memory because the MSB of the instruction memory address internally network wasn't in the net list wasn't connected, right? And we didn't find that in the verification because we only ever run small programs. So yeah, however much you verify, you always have a bug in there. 2016, Brexit happened, right? But two small villages of indomitable Saxons and Anglo-Saxons keep cooperating in SpiNNaker 2. Okay, who gets that reference? Us, right? Right, so we kept going after Brexit, which actually had a bit of a problem because there was all kinds of bureaucracy that kept coming in. They were outside the union and we couldn't send stuff back and forth that easily. Then this 2-year period had a major development. So 2017, we made the decision we would do a hybrid machine, kind of DNN plus neuromorphic. So we also put in the Mac accelerators. 2018, Steve had a SpiNNaker 1 machine operational. And here's a major one. Across that period, the HPP decided to cancel SpiNNaker 2, basically. I'll have some thoughts on that later on. That was actually the time also when they reorganized from Henry Markham's leadership to all this committee-based leadership. And then the neuroscientists just took over and they couldn't care less about hardware. So we got canceled in a sense. So I went from having 7 positions in the HPP to having a quarter position. So it was not quite kicking out, but close to it. Here we did a technology switch. So kind of 28 nanometer global foundries bulk was our bread and butter technology up to that point. And one of our startups, RACIX, have been doing a lot of design enablement for 22FDX. So basically at this point we said, yeah, let's switch. And Steve actually said, you guys are quite gung-ho about this. So he didn't really trust it. But in the end, came to be. 2021, we had the SpiNNaker 2 tape out. SpiNCloud Systems was founded to commercialize it. In 23, we had the first 48 node boards in the lab. And right now, we already got started on the SpiNNaker 3 design work. And autumn this year, the 5 million core machine is operational with all the Corona and whatnot delays we had in there. Actually, this tape out here was right during Corona times. So we managed a seriously huge process design tape out while everybody was sitting in lockdown in their flats, right? Here's another thing from the Dresden perspective. So this ecosystem buildup. It's kind of fun because we were working to something like SpiNNaker. Of course, we didn't plan it, but kind of just happened to be. So 2005, we got started with the Infineon guys on developing our own design flow, right? Design flow is very critical to really get stuff carefully verified, to know how the cadence and synopsis tools, how to plug them together, script around it, so you really get first-time silicon right. 2017, we started with the serial link communication. So that also very much was a building block of SpiNNaker. 2009, we founded Ray6. So Ray6 really had a huge impact, right? They had all this industry knowledge about how actually to do these systems from their contracts. They had this ABB, the adaptive body biasing, all kinds of appli blocks and design flow lying around. Actually, this design flow then was commercialized with Ray6. So, and this enabled us to really work together with the SpiNNaker guys, with the Manchester guys. So let's make chip. This is this kind of design platform. 2018, Ray6 had the adaptive body biasing. 2019, we founded Silicon Alley. So that kind of was a spin-off just coming out of the serial link design we did for the wafer and for the software-defined radio platforms. So basically the guys who did the links on SpiNNaker. So this is more automotive. This is what they first commercialized in the startup is this 1000 base T1 standard. But pretty much all the guys who did the link design for SpiNNaker and whatnot at the chair then took off and essentially did this one. Maybe here we also dabbled in Bitcoin mining chips a bit. Wasn't too successful, but we learned a lot about kind of thermal management, low power PCB design, rack design, etc. So it's like to come again, who's the supercomputing guy? Seymour Cray. He's got this quote, a lot of people can do a smart chip, but doing a smart system out of that is a totally different level, right? So that's what also kind of prepared us for that. Right, let's not get into too many details, right? Maybe just the differences, SpiNNaker 1 to SpiNNaker 2. So SpiNNaker 1 is entirely software defined, right? You just write your synapses, your neurons as code in the ARM cores. We kind of kept that flexibility, but we put in a lot more numerical accelerators, the Mac accelerator, X block accelerator, random sources, etc. So in the end, these things are fairly independent. They can run an entire layer of DNN, and then they go back to the ARM core and say, okay, what should I do next? So the ARM core is kind of more a manager of these numerical accelerators, those loosely coupled ones. And the ARM core enables us to do stuff in parallel, kind of. So you can run a DNN here. You might run a symbolic idea and code on the ARM cores right on top of it. Yeah, and lots of kind of, we made the computation very energy proportional. We made the communication very energy proportional. So that we really have a machine that confirms to the ideal kind of neuromorphic world in the sense that it only ever draws energy if it has to do something. So to give you one example, the SpiNNaker 2 boards, they have about as much throughput as an A100, but the A100, when you plug it in, takes 160 watts standby power. Our boards take 8 watts standby power, right? When you run them all out, the A100s take 400 watt, we also take 400 watt, but we really took great pains to get rid of all this background power burning stuff. And of course, the adaptive body biasing enables us to really go down to, in this case, 450 millivolts, but we actually can even go down to 400 millivolts. And you all know kind of power scales square with the voltage, so that gives us a big power advantage. All right. I had to find quite a lot of replacement money because human brain body would never cash out for that. As I said, they cancel us. So that was in German, 1 series Materialschlacht. getting all this, also the persons, this 100-person kind of design team distributed across our startups and the chair organized. So yeah, it's been one major piece of work. SpiNNaker is pretty big, so you get 10 to the 14 parameters that you can run there. And as I said, you can do quite some fun stuff, right? You can run an SNN, a DNN, and some symbolic AI layer right beside each other. Kind of really hybrid AI. That's what kind of DARPA calls the third wave of AI. You get the efficiency out of bi-inspiration, you get the everyday capability out of the DNNs, and you get something like anomaly detection, reproducibility out of the symbolic AI layer, because the symbolic AI layer helps you to seriously compress the internal dimensionality of the deep neural networks and have more of a rule-based layer on top that you can actually kind of access human readable. Right, we clocked it on various applications. Right. So what we're doing these days on SpiNNaker is, of course, some of the traditional stuff. So neuromorphics, SNNs, computational neuroscience, but that's not our bread and butter business because industry is actually not interested in the system. So Infineon has this AI center in Dresden, which is the main AI development kind of department inside Infineon. And I'm supervising 10 external PhDs at this Infineon Center. They all work on SpiNNaker for various things, from kind of room automation, car stuff, you name it, real-time management of power supply networks, etc., etc. So one thing we're doing these days, and we're pretty prominent on the Hirschberg ML conferences, so NeurIPS, ICML, ICLR, is we're kind of doing a cross, so event-based RNNs, DNNs, with lots of twists in there. So that's why I also called on to Owen's talk last week so much, because it also goes in the same direction. How do you actually kind of get these advantages out of the spiking side and really put them efficiently inside the machine? Yeah, then a lot of non-AI compute, right? We heard about optimization. We do quantum emulation on the machine. We do Monte Carlo sampling, constraint satisfaction. And one thing we also do a lot is drug discovery these days. Because drug discovery, only about 1/3 of the compute is actually deep neural networks. So GPU is actually overkill for that. Some other parts are really probabilistic compute heuristic. So you want to do electron density analysis to get a more accurate folding prediction. So that actually is more, as I said, kind of a Monte Carlo approach. Plus you want to do some more general type of code in there. So as I said, this stuff actually doesn't fit very well to a GPU. It fits very well to a hybrid, seriously weird hybrid machine that we have. Right, so gets back to the history stuff. Some impressions of the SpiNNaker 2 HPP journey with Steve. So that's Steve, myself, and Katrin Amunds. This was back when I had organized that money from Saxony, and we announced this on a big press event that we would continue with SpiNNaker 2. Somewhere in the same time frame, Steve visited. We celebrated his 64th birthday. So yeah, actually got Condito, what's that? The guy who makes the cakes. Anyways, gave him a picture, and he printed SpiNNaker on this eatable kind of wafer. Yeah. Steve and myself doing advertisement videos for Spin Cloud Systems for the startup. Some of you know Hector, right? He's been here last year. If Hector hadn't gone in the chip design and software direction, he would have made movie director. Hector just likes directing this kind of stuff or interviewing people. He's pretty professional about it. Yeah, we had lots of brainstorming sessions, for example, in Swiss Saxony, so outside town Dresden. That's a nice area. We invited the mentors, the guys over, and really trashed out what SpiNNaker is supposed to look like across kind of 3-day sessions in that hotel with parallel work groups, whatnot. Yeah. One interesting thing we had was also navigating the Human Brain Project. And this structure here, that was before they ousted Henry Markram, looks pretty clear cut, right? You could see who's doing what. That's the structure afterwards, right? When yeah.
They spent more money on the administration than the project itself.
Yeah, the trouble was really the EU, both the EU and the neuroscientists in the Human Brain Project, they weren't happy with Henry Markram. SpiNNaker very much had this top-down view. We wanted to integrate across all levels. The neuroscientists wanted to work a bit more bottom-up, right? They got Henry Markham to be ousted, and then there was a 2-year period when the European Union really started micromanaging us. We basically had to hand in reports every 3 months, so we didn't do anything but report writing, and they came up with this structure here. And actually, no one knew anymore where decisions were taken, right? So there were people on all these kind of committees, but I never could figure out afterwards where the money went, in a sense, right? It was just shuffling around. What was also quite interesting was planning around the HPP funding intervals. Despite the HPP being this 10-year contiguous project, it was cut up into really separate kind of legal, separate 2-year intervals, which also meant we had a lot of this, what you get in administration, right? Either we have to finish that money before the project runs out, or, right, otherwise it's lost, we can't take it over. So we had a lot of problems doing the tape outs in these 2-year intervals. And number of times actually the start of the next 2-year interval was delayed for whatever reason. So we had a lot of people where we need to find a lot of interim financing because it was up to a half-year delay and the university wouldn't cover for it, right? So we had a lot of fun actually kind of keeping people in their contracts despite that project always doing these weird things. Let's compare this to visual cortex, right? I think in the end, if you want a project like the Human Brain Project that does this kind of complexity, you probably have to have a similar complexity to the stuff you're analyzing. I'm just joking, but it was seriously weird in those days. Right, some random quotes. From Steve, consistency is more important than truth. That's on project reporting. So basically had to confirm to all the administrative guidelines the European Union was doing it and never mind what actually happened. So pretty much a lot of the reports were works of fiction. Another one from Steve, that's from the brainstorming sessions we had in Swiss Saxony. How many ARM costs do we have this week? Because according to our flow planning and how many accelerators we put in there, it kept changing. So in the project planning, we had anything from 110 to 200 cores. So the 152 cores kind of in the middle, but it wasn't really given why we have these many cores or not a different number. Here's another one from Steve. Any document that mentions the word quantum together with neuromorphics immediately loses all credibility. And here's the fun fact, Heidelberg now has a chair in neuromorphic quantum photonics. So that's about as many buzzwords that you can get in there. Richard Krakowiak at one of the HPP meetings came up with a new financial unit. So 1 markram is €1 billion, and then we were playing around like what, how many micromarkrams is the food we're eating today, right? And Steve, that's a very recent quote. Steve was kind of going into semi-retirement for as long as I've known him, but now it's finally final since last September. Basically he said, my wife is not too impressed with this retirement thing so far because still supervising students, still writing papers, still running his group at Manchester, but just not getting paid for it anymore, right? Here's a couple of quotes on SpiNNaker 2. HPP management, we don't need SpiNNaker 2. We already have a SpiNNaker system in HPP, right? So that was that when I asked them. And the U reviews, they were also fun. Why don't you build it with membristors? No one uses CMOS these days.
Why'd you skip the one above there?
Wait, No, I didn't skip it. So Karl-Heinz, I got a number of quotes from Karl-Heinz, but this one is fun. Dual use would imply we already have multiple use cases for neuromorphic hardware. In fact, we are struggling with the first use. I actually have a second one from him a bit later on. He basically said, we cannot omit dual use because we intend to do some, the military can use anything that's useful and we don't intend to do anything that's useless, right? So dual use is in there. And actually, these days you have to put some ChatGPT in here. And ChatGPT was pretty good. So we had papers to go with that event in January. And this is from some longer passage I did from ChatGPT in the paper. We show Steve's retirement will be anything but idle, unless, of course, he's experimenting with low power modes in his hammock. Here's to a retirement filled with armchairs, cashing in on life's pleasures, and branching out into new adventures. Which is actually a pretty decent piece of humor getting in this micro processor kind of speak, right? That's from this happening in January, right? There's Steve, there's myself. Some of you might know Piotr, of course, and the rest is basically academic colleagues and ARM colleagues. Can't come up with her name, but that's the lady who co-invented the ARM so the architecture with Steve. So a lot of history going on there. And as you can see from the picture, I'm quite kind of lowering the average age there. Right, and that's already pretty much the end. Yeah, SpiNNaker story continues. So of course, this is an old picture from Steve's group a couple of years ago. A lot of them have left, but these two guys here, John Goodacre and come on, Italian guy, no, bad with names. Anyways, they two are building up this group again. So we already discussed 2 weeks ago a lot of cooperation possibilities there. That's my group in Dresden, and this is SpiNCloud Systems. And actually, this is already outdated. This is last autumn. There's now about double that number of people in SpiNCloud Systems. So if you're looking for a job, we're hiring. Yeah, that's the roadmap, right? So that's pretty much the SpiNNaker 2 roadmap. So now we're here. And now, so across all the kind of prototype chips we did here. And then, as I said, aim is to go towards SpiNNaker 3 and even more kind of general event-based compute platform. That being said, I haven't yet secured the funding for that SpiNNaker 3 development. So talking to a lot of politicians on that. It's been surprisingly difficult to get it. Yeah, there's a lot of early SpiNNaker 2 adopters, you among them, right? So there's all these kind of academic partners. We actually use SpiNNaker 2 in teaching already as a kind of novel AI platform. We get a lot of big companies in there and a lot of startups actually that are starting to use SpiNNaker. A lot of them that come out of this tactile internet environment in Dresden, these big projects, they want this real-time kind of very massive AI processing. Yeah, and now feel free to chunk rocks at me. Who gets that reference? So that's also Monty Python, right? This is Life of Brian.
Yes.
When they were stoning the guy. Yes?
First comment I'll say on your, by the way, I like your image. I actually have a PhD student of mine actually in his PhD defense with that picture, the full picture actually.
Okay.
That was, so yeah, it's hilarious. The second question here is like, by the way, nice material. If you were to do a SpiNNaker 3, what process would you do it in, and like what would you be trying to aim to go around here at that point? Because like he's running pretty nicely in 22, right? 22 nanometer.
Okay.
So I'm just curious about that.
Yeah.
It's a fascinating question of roadmaps.
So architecture-wise, I have to admit we went into SpiNNaker 2 without a lot of system level knowledge, right? Because Steve got a bit sidetracked into supporting all these small systems. He never got a lot of benchmarks running on the big system. So we basically didn't know. We went ahead with SpiNNaker 2 design, but there's some very rough estimates what we would need. So this time around, we have these big benchmarks. So definitely that's one major part of what will flow into SpiNNaker 3, really this use case experience at that scale. Because we were actually shopping around Capocaccia, if you remember those days, and trying to make guys, the SpiNNaker users, tell us what to do, and there was kind of a bit of silence there, right? So we just went ahead. This time it's going to be slightly different. The other thing is architecture-wise, of course, Steve had this system level knowledge. We were these bottom-up kind of processor system designers. So we kind of met in the middle, but of course it isn't the same as if you really design this machine in one go, optimized across all levels. So that's also something we're definitely doing different for SpiNNaker 3. We're actually already building up a huge simulation model for SpiNNaker 3, which has some power numbers behind it, has some numbers for the communication behind it, etc., and where you can kind of virtually run algorithms and really system design the machine in a sense. So that's on the architecture level. In terms of the technology, essentially, it will be FinFET. It will be about as advanced a FinFET node as I can afford. So ideally, I mean, the startup is already pretty good. They're doing decent business. So ideally, we're going to split that. We do a tape out. So this the startup SpiNCloud Systems basically will do a new design every 2-3 years, kind of streamlining SpiNNaker 2 and derived systems for commercial use cases. And we just, SpiNNaker 3 is going to be another 16-year project. So we just piggyback on one of the quarter mass tapeouts, then essentially, so we share the tapeout mask. Because in the end, with all this adaptive body biasing we did here, we were about comparable with a 7-nanometer FinFET, but not better, right? Most of this comes in at the architecture level where we're really good. So by having this cool architecture and still going to a 2-nanometer FinFET, then of course we just by that we gain almost a factor 10 then in performance. So we're trying to keep, of course, a lot of the advantages here. So it's going to be tricky to get a FinFET technology to be energy proportional, right? And a FinFET technology, you always have a huge because you need to over-design your system, right? Not like adaptive body biasing, where we could narrow the VTH spread of the transistors to a very thin distribution, and we could basically cut off the supply voltage very close to this VTH variation. The added effect of that was we actually had very little leakage power. So the 22-nanometer design here conforms very much to this CMOS idealism that a circuit only takes energy if something toggles. And it's going to be tricky designing this kind of system also in FinFET. So definitely we won't max out the operating frequencies, because that's one thing. I mean, SpiNNaker, it's got 300 and 150 megahertz operating modes in this DVFS. So when you switch around between the voltages and the frequencies, and if you go back from these gigahertz frequencies, you actually can define your system a lot better towards this idealism, kind of very low leakage bottom and really just a dynamic power draw.
And I can appreciate the design issues.
Just don't ask. I mean, with the adaptive body biasing, there is so much voodoo. It's getting so multi-dimensional optimizing. There's maybe 2-3 people at my chair who actually know what they're doing there.
It'd be fun to talk about more about
if
you ever want to.
Sure.
Yeah, so people just throw rocks. One question I would have is like, this is for a business, right? So the business use case, what people would care about is how many dollars do they need to pay for solving a problem. And Amazon, I don't know how much Amazon Cloud Service really costs, but someone was saying like 150 per GPU or some number like this. So why do you think SpiNNaker will be cheaper for people to use than just using a data center as a bunch of GPUs? Like, what is the knob that makes it cheaper? Like, is it just like savings on energy and like?
No. I mean, this was one journey we had across the last 2 years, right? I mean, really figuring out what the data centers, what the use cases are. So one thing we're definitely not going to be doing is trying to replace NVIDIA. Because there's any number like TensorRT, like GraphCore, SambaNova, you name it, they all tried it with way more financing than we had here, and they all basically didn't make it, right? A lot of them, like GraphCore, pretty much went bust. So this is not a GPU replacement machine. That's what I said. It's a weird architecture. I always call this kind of a GPU, a CPU, and a quantum computer all rolled into one, in a sense, with a probabilistic compute. So it works best. That's why we figured out if you have these kind of hybrid systems. So one thing, what we're doing a lot with defense industry these days is putting a symbolic AI layer on top of deep neural networks. So they can do anomaly detection, airspace supervision, that kind of stuff, and at real time. That's one thing that SpiNNaker is designed for. A lot of the GPU systems are not designed for. They're designed with the communication links for high bandwidth throughput, but not necessarily for quality of service, like really keeping to this millisecond. So as long as we have, of course, our bandwidth, nothing exceptional, right? So if we flood that, then the system will get slower. So the algorithm that needs to run on SpiNNaker needs to be sparse, kind of locally dense, globally sparse, both structurally and in time. But then you can ensure this quality of service. And then you have a massive machine, for example, for defense, that can do airspace supervision at kind of whatever, at almost global scale, or at least the smart city guys are also pretty keen on us, because that's about the old machine that can run a smart city like Neom in real time, right? This is like an edge AI system that's very much built towards real-time performance, but at cloud scale. So that's basically it's smart city, it's defense stuff. It's the drug discovery, because drug discovery is such a nice hybrid system, problem. The optimization also very much goes towards that. The optimization we're actually showing they'll be pretty fast, about a factor 60 faster than if you run this with a standard optimization tool on a comparable processor. So what we figured out in the end is that energy efficiency is actually a secondary thing. It probably will become more prominent in the next years, but what really sells this machine is if you're faster on kind of specific use cases. Again, the drug discovery, if you do personalized medicine, there's a guy in Dresden, and he's a second chair in Vanderbilt, who's doing that quite a lot. So he's working also with the Google guys there. And these big GPU centers, his drug discovery problems, it takes weeks to do, basically, to design a specific molecule. Before that, the guy will have died, A, and B, weeks of GPU runtime, no health insurance on the planet is gonna pay for that, right? And with SpiNNaker, we get this down to hours, and ideally we get this down to minutes. And then this becomes a business case, because then it's a kind of, this machine is then a lab machine that gets amortized across a lot of patients, and not like, you need to pay millions just to design a drug for a particular group of people if you want to get that specialized. So we're very much focusing on kind of special use cases that really play to the strengths of the machine. Definitely not a GPU replacement. So coming back to the money question, we're not trying to be cheaper. We're trying to be more efficient, and the pricing for the hardware and the cloud hours and whatnot is about comparable to what you get for GPUs, right? So we're not trying to undersell anybody. People really pay the same price they would for GPU, but we solve a problem for them that the GPUs can't solve.
So how do SpiNNaker 2 and SpiNNaker 1 compare in terms of power and system size that you can simulate?
So the rough estimate is that about one of the old 48 node boards on SpiNNaker,
full rack system.
Yeah, no, but just comparison, one of the 48 node boards of SpiNNaker 1 is now about one chip. That's about the capability. So we're really talking about a factor 50 scaling about-ish. So if you can run about 1 billion neurons on SpiNNaker 1, it's about 50 billion neurons. So really going towards brain scale on SpiNNaker 2.
And power?
Yeah, that's actually not so good. SpiNNaker 1 draws at most 100 kW. The maximum, that's probably, if you run really all out, SpiNNaker 2 is about 300 kW. So we actually had to put in 500k euro on construction money, just reinforcing the cooling and everything in that room at TU Dresden. We put it in. So that was also, it kept kind of snowballing. Yeah, we need that construction, we need that construction, and all of a sudden it was 500-600k in construction money that TU Dresden had to shell out for that machine.